Hello, hello, everybody. Let's look at 9.6 here. This section is about something known as Gaussian elimination. So we kind of went on a little side trip here. We were starting chapter 9 and we were talking about systems of equations. And then we sort of went off on a tangent and spent a lot of time talking about matrices. Well, now what we're going to do is we're going to kind of circle back around and put together what we know about matrices and then turn that into a strategy or technique for solving systems of equations. So for this first problem, they ask us to write the augmented matrix for the system. So this is not super difficult. It's just you got to understand what they mean and what it is that they are talking about. So if you're going to write an augmented matrix, what you're going to do, you're going to make yourself a matrix here. And so each column is going to be for each variable. So you're going to have a column for the x's, you're going to have a column for the y's, and you're going to have a column for the z's. And what we're going to do is we're just going to put in the number or coefficient of each of the equations here. So like for the x's, if there's no number there, that would just mean it's a 1. So this would be 1, 2, 1. For the y's, you have a 2, that would be -1, and then -3. And then for the z's, you have -z, that's going to be -1. 2z, you have a 2. 3z, you have a 3. And then here's where the augmented part comes from. This gives you just as like standard 3x3 matrix. And then what you usually see is they put a dividing line right here. This is showing basically where the equal sign goes. And then here you've got 3, 6, and 4. So that is it. That is the augmented matrix. It's like a 3x3 matrix, and then it's augmented, meaning they like expanded it. They made it bigger by attaching an additional column for the numbers that each of the equations are equal to. So that is an augmented matrix. Now, what we're going to do with this is we can actually, before we get to how you solve using an augmented matrix, next what we're going to do is we're going to do this process in reverse. Here they give us an augmented matrix, and then what our goal is going to be is to turn it back into a system of equations. So like before, you're going to have a column for x, a column for y, and a column for z. And then where you have this dividing line, that's basically where the equal sign is going to go. So if you're going to turn this into a system, the x's, you've got 1, 2, -3. If it's a 1, usually you don't bother to write it. So you're going to have x, 2x, -3x. So all of those numbers get an x attached to them. Next, you're going to have the y's. You're going to have a -3y, a -5y. You do need to put a plus sign here. Don't just write 3x, 5y. You do need a plus or minus sign separating each of them. Let's make this look a little more y-ish. And then finally, for the z's, you're going to have -5z. You're going to have -4z. And then finally, you're going to need to put a plus sign again, +4z. This dividing line tells you where the equal signs go for all of them. And this is going to give me -2, 5, 6. So there you have it. That would be the system of equations that would correspond to that augmented matrix. Now, we've not gotten into how we would solve this just yet. We're mainly just focusing on, can we do the basic stuff? Can we go back and forth between a system and a matrix? I hope you'll agree with me that doing that much at least is not too terrible. So then Gaussian elimination, named after a mathematician named Carl Friedrich Gauss, he came up with a strategy by which you could take an augmented matrix and use it to solve for a system of equations. And the key to the strategy is this. The goal is to get ones along the main diagonal, is what that's called, in addition to having zeros in the bottom left corner. And then you can solve the system of equations by having this equal some number. You'll have 1z equals something. You can then find the value of z, jump up to the middle equation, plug in the value of z, and use it to solve for y. Then once you have z and y from the middle equation, you go back up to the top, plug in a value for y, plug in a value for z, and then you can use that to then solve for x. So it's a strategy by which you can solve a system of equations. And this is based on row operations. So the row operations you can do, you can add or subtract rows. That is one row operation you can do. You can multiply scalars by everything in the row. And then something else you're allowed to do is you are allowed to transpose, or they say interchange rows. So basically change position of rows. So what that means is you can take the second row and make it the third row. You can take the third row, move it up to the top, and it can become the first row. Something like that. Something else that I'm going to observe for how this strategy is going to go, and this is kind of like what they're talking about down here. They're saying use row operations to obtain zeros down the first column below the first entry. So what we're going to want to do is we're going to want to turn this into a zero, then turn, let's try that again. So we're going to kind of go like this and then like this. So we want to make this a zero first, that a zero second, and then this will be a zero last. So let's maybe try to make that. So the goal is to have that be a zero, then make that a zero, and finally make this one right here a zero. Getting those to equal zero first is the hard part. That's what you want to start with doing. You can then use scalars to basically divide to make any of the main diagonal values a 1. You can usually do that afterwards, and that's not too challenging. Getting them to equal 0 is the real trick to this. So let's actually try this with some actual numbers, and maybe it'll make more sense just what on earth I'm getting at here. So we'll not just be talking about like how we do this in the abstract, but look at how this process is actually supposed to work. So we're going to kind of start off easy by doing just a 2x2 matrix here before we kind of step up to doing like a 3x3 one. And I mean, you could do, and the sky's the limit. I mean, you could do like 4x4s and 5x5s, and you know, you could scale this up as big as you want. But to start things off, we'll just do like 2x2. So if we write an augmented matrix here, we're going to have 2 and 1 for the x's. We're going to have 3 and -1 for the y's. And then we're going to put a line, and then we have 6, and we're going to have a half. So the goal is to have 1s on the main diagonal, a 0 down here, and then that will be something, this will be something, and then this will be something. But the goal is to have 1s on the main diagonal, and then we want to turn this into a 0. So here's what we can do. Kind of like what we did when we were doing systems earlier. What I'm going to do is I'm going to number these off. I'm going to call this row 1. I'm going to call this row 2. And so what I'm going to do to turn this number into a 0 is I'm going to do the following. If I were to do -2 times row, sorry, I'm already messing up. If I were to do a -2 times row 2 and then add row number 1, that's going to be my new row 2. So I'm going to change row 2 and do the following. I'm going to do -2, and I'm choosing -2 because I want to have it match the +2 that's up here. Because just like when we were doing elimination, it's the same general strategy of what we're trying to do. The goal is to get opposite numbers to make these so that they cancel each other out. So what is this going to be? If I do, let's do it off to the side here. So if I do -2 times row 2, that's going to give me -2 times 1, and then it's going to be -2 times -1, and then -2 times a half. So we multiply all that. This is -2, this is +2, that's going to be -1. This is the multiply step. Then with row 1, we're going to do 2, 3, and 6. That's row 1. And what we're going to do is we're going to add these up and see what we get. That'll be a 0. That'll be a 5. That'll also be 5. So now the matrix looks like this. I didn't change the first row. I still have 2, 3, 6 up here. The new one is going to be 0, 5, 5. Okay, so that's the first step. I got the bottom left corner into a 0. My next goal is going to be to turn the main diagonal into 1s. So what I'm going to do, this is now row 1, this is now row 2. What I'm going to do is I'm going to do 1/5, also known as dividing by 5. I'm going to do 1/5 times row 2. That will be the new row 2. So if I do 0 times 1/5, that's just 0. If I do 1/5 times 5, that is going to be 1. And if I do 1/5 times the other 5, which is this one over here, that will give me 1. So now what I have is this. I have 2, 3, 6. I have 0, 1, 1. Let's pick up the story from there. Okay. So now what I'm going to do Again, this is row 1, and this is row 2. Now my goal is to make this upper number, which is currently a 2, into a 1. So the way I'm going to do that is I'm going to do 1/2 times 1, and then that will equal the new row 1. So that's where I'm going to put my answer. So what's this going to be? I'm going to do 1/2 times 2. I'm going to do 1/2 times 3. I'm going to do 1/2 times 6. This is going to give me 1. This is going to give me 3/2. This right here is going to give me 3. So then if I put this all together, I get this: 1, 3/2, and then 3. And this is 0, 1, and 1. So now here's what I'm going to do. I'm going to turn this back into a system with X's and Y's in it. So then when I do that, I get X plus 3/2 Y equals 3. If it's a 0, that means there is no X at all. If there's a 1, then it's just a plain X, but the X is still there. If it's a 0, there is no X at all. This is just going to be Y equals 1. You could put, like, I guess if you wanted to, you could say 0x plus that, but that just, multiplying X by 0 doesn't do much. It's going to collapse down into Y equals 1. So guess what? We already know what Y equals. We're actually halfway along to knowing the answer. What we're then going to do, that's the whole point of doing this reduced row, or this reduced echelon form is what this is called. This is called reduced echelon form. In case you see that term thrown around, that's what they're talking about. Reduced echelon form. So by having it set up this way, we know immediately what Y is. Now all we need to do is plug in that value into this top equation. That's going to be X times 3/2 times 1 equals 3. That's X plus 3/2 equals 3. And you can subtract that. And fun fact, 3/2 is 1.5. If you do 3 minus 1.5, you get 1.5, which means X is also 3/2. So we now know the values of X and Y, and we can write our solution as 3/2, 1. And there you go. That is the actual answer. So it's big picture, it's just another strategy, a slightly different approach for how to go about solving a system of equations. And the sort of general goal is to separate out the variables from the numbers and mainly just focus on the numbers themselves. What are the numbers doing? What can you do to the numbers to make them work out the way you want them to? So here is another one. They say use Gaussian elimination to solve this 2x2 system of equations. So again, we're going to use the same approach here. So first we're going to write this as a matrix. So we've got 2, 4, 1, 2. Draw our line right here, and then we've got 1, 6. Okay. So the first thing we want to do is turn this number here into a 0. That's the first goal, because you're always going to want to turn your bottom corner into zeros first. That's usually the harder part. And then once you've got the zeros in position, it's pretty easy to just multiply a scalar to shrink the numbers down to a 1. That's not the big deal. Getting the zeros is the the challenge with this. So here's what we're going to do. Like before, we'll call this row 1, and then this is row 2. The goal is to make this a 0. So if we were to do -2 times row 1, and then add row 2 to that, and then our goal, we will put that in row 2. So let's see what we end up with. You're going to have -2 times 2. You're going to have -2 times 1. You're going to have -2 times 1. So this is multiplying -2 by the first row. That's what we're doing. So when we do that, we get -4, -2, -2. Okay, fair enough. Then what? Then we're going to take the second row, which is 4, 2, and 6, and then we're going to add those together. By design, that gives you a 0, that gives you a 0, and that gives you a 4. So what ends up happening here, we've got 2, 1, 1, and then you've got 0, 0, 4. Now, this is a bit of a problem because the goal is to have that number be a 1. And so there's not really a way to use a scalar to turn that into a 1. Furthermore, if you were to write this as a system, if you were to turn it back into a system, here's what you'd get. You'd end up with 2x plus y equals 1, and then 0x plus 0y equals 4. 0 times x is 0, 0 times y is 0, and fun fact, 0 plus 0 is 0. You get the fun statement that 0 is equal to 4. This is a very elaborate way of saying this has no solution. Or you could also use the term inconsistent. If there is no, it would help if I could spell. The term for a system that does not have a solution is inconsistent. Fun fact, these are, if you were to graph these as equations of lines, it's going to turn out that they are parallel lines and they are never going to intersect because there is never going to be a point where they meet. So if you ever end up with something like this, where you've got a pair of zeros down there, that's going to be an inconsistent system. It is not going to have a solution. Okay, let's see what else we have going on here. So then they say solving a dependent system. So we just saw one that was inconsistent. Let's see what happens if it is dependent. So you've got 3, 4, and 12. Here we have 6, 8, and 24. So here is row 1, here is row 2. You've got a 6 and a 3. The goal is to turn this into a 0. So what we can do is we can do -2 times row 1, and then add row 2 to it, and put our answer in row 2. So when we do that, what we're going to end up with, we're going to have -2 times 3, we're going to have -2 times 4, we're going to have -2 times 12, we're going to get -6, -8, -24, and then we're going to add to that row 2, which is 6, 8, and 24. And lo and behold, you're going to end up with zeros across the board, which means we now have this. We're going to have 3x plus 4y equals 12. And then you have 0. I don't know why I put a bracket here. Hold on. All right, let's try it again. 0 plus 0 equals 0. So this is a dependent system. There's a reason I don't teach English. All right, dependent. There we go. This is a dependent system, which we kind of sort of knew because the example was conveniently labeled as a dependent system from the get-go. So what this then means is you want to solve this for, we're going to take 3x plus 4y, and we're going to equals 12, and we're going to solve for y is what we will do. So we will subtract 3x from both sides. That gives you 4y equals negative 3x plus 12. Divide everything by 4. And you will get this, y equals negative 3/4 x plus 3. So then your solution would be x, comma, negative 3/4 x plus 3. So that is a dependent system. The solution depends on what the value of x is. And if I know a value of x, I could then find a corresponding y value to go with it. But that's part of the logic of why they call this a dependent system. What the answer is depends on knowing one of the numbers to begin with. And since we have no way of knowing any particular value of x to begin with, it's as I say, it depends on whatever x is. And we don't have just one specific value of x that we can use because there's not just one right answer. Any point on this line would be a solution. Okay, if memory serves, we finished this with some 3x3s. Yes, here's a 3x3 one. And then we got a word problem. Okay. All right. I think maybe what we can do is save the last bit because I can tell you doing one of these problems does kind of sort of take a while. So I think what we're going to do is we're going to call it there for tonight. And then we will pick up with this when next we meet on Tuesday. So I'm going to stop there.